Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7cc, Lesson 8, Samples of Two Populations. All right, so this is really kind of getting into the heart of what much of statistics is about, which is, it's about answering statistical questions, right? And remember that when we answer statistical questions, we're often trying to answer questions about populations. And many times what we want to do is we want to compare two populations, right? Think back to our discussion about simple experiments where we had a control group and then a treatment group, right? So our two populations are, what if we do nothing at all and what if we, kind of treat, right? But almost always when we're comparing two populations, we actually have to compare two samples, right? One sample drawn from population A and one sample drawn from population B. And why do we have to do that? Well, let's look at exercise 1 for a moment. Julian is trying to answer the following statistical question. Are children who are 15 years old taller than children that are 8 years old? Explain why Julian would need to use samples to answer this question instead of the populations involved. Well, let's talk about this together, right? This should be pretty straightforward, right? Julian is trying to answer a question about all 15-year-olds and all 8-year-olds. And to put it mildly, right, it would be impossible to get every height in each population. It just wouldn't be possible, right? There are far too many 8-year-olds, far too many 15-year-olds. Maybe if, Julian was only interested in the heights of 15 and 8-year-olds in a particular school, in a particular town, maybe it would be possible. But even then, it wouldn't be likely to be very possible. So the point is, Julian would have to take samples in order to say something about this. Now, obviously, like for most people, you're like, well, of course 15-year-olds are taller than 8-year-olds, right? But not every 15-year-old is taller than every 8-year-old, okay? So that's where samples come in. Now, in this particular lesson, we want to explore how different samples Julian might take from the two populations might tell us information about the populations. For this lesson, we created two hypothetical populations, each with 200 members. Now again, keep in mind that if Julian is really trying to answer this question, right, are 15-year-olds taller than 8-year-olds in general, right, then the populations that he's talking about have far more than 200 members. They have millions upon millions of members, right? There are millions of 15-year-olds in the world. There are millions of 8-year-olds in the world. Even if Julian limited himself down to just the 15 and 8-year-olds in the United States, there would still be millions of 8-year-olds and millions of 15-year-olds. So far more than 200. But we had to kind of limit ourselves a little bit. Now, in this particular lesson, I've given you these diagrams on a separate sheet of paper. And here we've got a distribution of 200 heights of 8-year-olds, and we've got a distribution down here of 200 heights of 15-year-olds. Both distributions are reasonably symmetric, right, with some distinct peaks, some tails that extend in both directions, so they're both pretty well behaved. All right, and let's take a look at the first exercise based on this. Exercise number 2. Use figure 1 to answer the following questions about our populations. Letter A. How much greater is the mean height of children who are 15 than the height of children who are 8? So this is pretty easy. Take a moment, take a look at the population statistics here and there, and then answer this question in letter A. All right, well, I've given you a lot of space to do a very small amount of subtraction, okay? The mean height of 15-year-olds is 65 inches. The mean height of 8-year-olds is 50 inches. And so, at least in this case, right, the population of 15-year-olds has a mean height that is 15 inches greater, right, than that of 8-year-olds. Right, that's like over a foot taller, okay? Now, letter B. How does the difference between the two means compare to the mean absolute deviations of the two populations? Okay, now let's kind of talk about this together. One thing that's going to be true in this entire lesson is of the two populations, I'm going to keep their MADs either equal or roughly equal. In this case, both of those MADs are 5 inches, right? So both mean absolute deviations, right? And that's the average amount that a data value is away from the mean, is 5 inches. So the difference in the two population means, which is right up here, is 15 inches. So the difference, right, the difference of means is 3 times the mean absolute deviations. In other words, the difference between the means of the two populations is much larger than the variability within the populations themselves. All right? And that's going to become important for us eventually. Let's take a look at the last part of this problem, letter C. Are there any children who are 8 years old that are taller than children that are 15 years old? Explain how you can tell from the plot. Well, the answer is absolutely yes. Right? I mean, just consider the tallest 8-year-old right here. Right? That person, or the two tallest 8-year-olds, the tallest 8-year-old is much taller, right, than the shortest 15-year-old. Much taller. 65 inches versus, I think it's 48 inches. But really, you can tell that there are 8-year-olds that are taller than 15-year-olds because there's overlap, right? There's this overlap between the two distributions. Right? And it's in that overlap where you get 8-year-olds and 15-year-olds that are the same height, right? So if I just went to, like, let's say 60, right, then I've got 3 8-year-olds that are 60 inches tall and more than 3 15-year-olds that are 60 inches tall, but there we've got them that are the same height. The point is, even though it's very clearly obvious that in these two populations, right, that 15-year-olds are in general taller than 8-year-olds, there are definitely 8-year-olds that are taller than some 15-year-olds. Okay, so it's not as clear-cut as just, sure, 15-year-olds are taller, right? So let's take a look at exercise number 3. If we took a sample of 20 heights from each distribution, would it be possible to find a sample of 8-year-olds that had a greater mean height than a sample of 15-year-olds? Explain. All right, well, think about this for a second. Pause the video, and could it occur that if I took 20 heights from this distribution and 20 heights from this distribution, could I actually get a scenario, and think back to our last lesson when we were doing samples of populations, could I get a sample from this that had a greater mean height than a sample from that? Pause the video for a moment. And again, the answer is absolutely, right? Yes, right? In fact, one way to do it is just to take the 20 largest 8-year-old heights and 20 smallest 15-year-old heights, right? So like literally, if I just kind of grabbed, let's say that's 20 and that's 20, it's probably not, but let's just say that they are, right? This grouping would definitely have a higher mean than that grouping. Now, if you're saying to yourself, well, yeah, but I mean, how likely would it be that if you did a random sample of 20, that you'd randomly pick these exact 20 and these exact 20? Well, that's a fantastic point. And that's actually why we want random samples, because if we take random samples, then it's most likely that the random sample from this distribution will have a smaller mean or a lower mean than this sample. Remember, I'm not trying to answer the question, are 15-year-olds 15 inches taller, on average than 8-year-olds? That's not what I'm trying to answer. I'm just trying to answer, are 15-year-olds on average taller than 8-year-olds? So how do you answer that question? Well, you answer that question by taking samples. So let's take a look at exercise number 4. The following table shows the results from 10 random samples of size 20 each. So let's talk about this a little bit. Now, we could have, like in the last exercise, we could have actually had you do random samples from one population and random samples from the other population, right? But that takes a lot of time. So we did that for you, okay? And these truly were random samples. We took, a random sample from, the population of 8-year-olds, then another one from the population of 15-year-olds, okay? And these are the two mean heights that we got. Then we did it again, 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 okay? And we did that for you to save a lot of time. Now the first part of this problem then says, letter A, fill in the last column with the difference between the two sample means. And by that, what I literally mean is I want you to do mean 2, this one, minus mean 1, this one, for each one of these. Now remember, our population difference was 15 inches, right? So when we looked at the mean, the population mean of the 15-year-olds minus the population mean of the 8-year-olds, we got a difference of 15 inches. But what will our samples show us? Pause the video now, definitely use your calculator to speed this up and do that subtraction. Take a moment. All right. Well, again, it's pure straight up subtraction. We're not going to show that on the calculator or anything like that. And there they are, right? 15.2 was our first difference, 15.7, 18.2, 13.5, 18.1, and notice quite a bit of variation, right? Some of them are quite close to the actual population difference, like this first one, 15.2. Some of them are much farther away, like this 18.1, or even on the low side, right? The 13.7. But take a look at B, because this is very, very important. Letter B. How do the numbers in the final column of the table support the idea that children who are 15 years old are taller, on average, than children who are 8 years old? So why do these numbers support that hypothesis? That's what we would call it, that 15-year-olds on average are taller than 8-year-olds. Pause the video and write something down. Well, partly, think about this. What would have happened had one of these been smaller than one of these? Then when we did this minus this, we would have gotten a negative number, right? Don't forget that about subtraction. 5 minus 3 is equal to 2 because 5 is larger than 3. But 3 minus 5 is equal to negative 2 because 5 is larger than 3, right? So the numbers in this column support the idea that the mean height of 15-year-olds is greater than the mean height of 8-year-olds because all the differences are positive. All the differences are positive, right? None of them are even close to 0. Right? None of them are even small. They're all pretty significantly large, which means in every single case, the heights of the 15-year-olds far surpassed the heights of the 8-year-olds in these samples. Very important. Therefore, we'd have a lot of confidence, right, in saying, especially after taking that many samples, that we're pretty sure in the population as a whole, the population of 15-year-olds has a higher average height than the population of 8-year-olds. Not a great surprise, I get it. 15-year-olds generally are taller than 8-year-olds, right? Sophomores in high school are taller than whatever 8-year-olds would be. Second graders, whatever. All right, let's take a look at exercise number 5. Tessa would like to answer the following question. Are people who go to drama movies older than people who go to action movies? Why must samples be used in this situation instead of the populations? All right, I think you know the answer to this one, but pause the video now and write it down. It's pretty easy. You simply can't get every age of every person who goes to every drama and every action movie. You just can't. There is no way to get every age of every person who attends every drama or action movie. Right? Just no way. Right? It's not possible, right? There's movie theaters all over the place. They're showing all sorts of movies. Just would be impossible to do that. Okay? So, yet again, what we're going to do is we are going to look at a hypothetical situation. All right? Let's take a look at exercise number 6. Use figure 2 to answer the following questions about the two populations. So now, right, let's back out just for a minute. We've got these two populations, right? One is a population of ages of people that went to an action movie, and one is a population of ages of people that go to a drama movie, all right? And we've got all their statistics, like in this population, right, the mean age of people that go to action movies is 50 years, the MAD is 10 years. And in the drama movies, the mean age is 55 years, and the MAD again is 10 years. I designed these populations so that the MADs were the same. All right? So letter A, just like before, how much greater, should be greater, how much greater is the mean age for those who attend drama films compared to action films? Let's put a little ER on there so it's now grammatically correct. How much greater is the mean age for those who attend drama films compared to action films? All right, well, this is simple, right? Just like before, we're talking about a simple subtraction, right? Those who go to drama movies are 55 years old. Those who go to action movies are 50 years old. So those that go to dramas are 5 years older. Now, again, these are the populations. These are what we would not know if we were really doing or trying to answer our statistical question. We would not know this. If we did know it, we would have the answer to our statistical question immediately. All right. Now, letter B. How does the difference in A compare to the mean absolute deviation of the two populations? All right. So in other words, we looked at this before in our first example, right? We had a difference in population means of 15 inches and MADs of 5 inches. So the difference in the population means was 3 times greater than the MAD of both populations. But here, what's the relationship? Pause the video now and think about that a little bit. All right, in this situation, right, here the difference is equal to 5 years. The MAD in both cases is equal to 10 years. So, 10 years. So the difference between the two means is only 1/2 of the MAD. Now, this is interesting because what that really is saying is that the difference between the mean ages is actually smaller than the variation within the data sets themselves, okay? So the average variation within the data set, as given by the MAD, is actually more than the difference between the two means. And we're gonna see that that has a huge effect on what happens when we start to take samples from these two populations. All right, so let's get into it. Just like before, what we did is we randomly sampled from these two populations. We took, 20 each from these populations, and we did it 10 times, and each time we calculated the mean age of those people going to the action movie and the mean age of those people going to the drama movie. We kept doing that over and over and over again. So just like before, what I would like you to do in letter A, or in exercise 7, sorry, is I'd like you to do that subtraction. Again, feel free to use your calculator and always do this number minus this number. This number minus this number, this minus this number minus this number, etc. Pause the video now and go ahead and work out those differences. All right, so let's take a look at them. Here they are, right? Now this is kind of fascinating, right? Remember, the differences between the two populations were equal to 5 years. So this first one gave us 3.2 years, 2.4 years, 7.5 years, negative 1.1 years, right? That was a negative because we had 52.1 minus 53.2. And then 8.1, then another negative, negative 1.4, 5.2, another negative, negative 0.4, etc. Okay? All right, exercise number 8. Look at the differences in the sample means, the final column of the table. Letter A. Do all of the values in the final column support the idea that the average age of people going to drama movies is greater than the average age of people going to action movies? Explain. All right, so just like before, does every one of those numbers here support the idea that people who go to drama movies are older than people who go to action movies? Pause the video now and try to answer that question. Well, and the answer is no, because some of them are negative. You know, and of course, what are the negative ones really doing? The negative ones in those situations are situations where we took a sample and the mean age of those going to a drama movie was less than the mean age of those going to the action movie, right? 52.1 years is younger than 53.2 years. 50.4 years is younger than 51.8 years. So the answer here is definitely no. Whoops, went a little bit too far. Definitely no. Some of the differences are negative. Some of the differences are negative. All right, a very similar question, letter B. Would any of the trials lead you to believe that the mean age of those attending action movies is greater than the mean age of those attending drama movies? If so, which ones and how many? Again, this is a direct extension from A, so pause the video now and see if you can answer this question. All right, well, sure, right, and it's the ones that we pointed out before. So first, would any? Yes, right, which ones are they? Well, they are trial number 4, right? Trial number 6, and trial number 8. So you can imagine, right? Let's say that you had to do some kind of statistics project for school, and this was your question you came up with. You kind of hypothesized that people that go to action movies just tend to be a little bit older than people who go to drama movies. So you go out, maybe you sample, 20 people coming out of a drama movie, 20 coming out of an action movie. You calculate their means and you find this, right? You find, oh geez, the mean age of people who, went to that drama movie was actually lower than the mean age that went to the action movie. Completely contradicting, right, what your hypothesis was. You went in thinking, people going to drama movies, they're going to be older than people going to action movies, right? So there are 3 of them, and they happen to be 4, 6, and 8. Trials 4, 6, and 8. Now think about that for a moment. 3 out of the 10 trials gave us misleading results, and they were misleading. The population of people going to drama movies had a higher mean, a higher average age, than the population of people going to the action movies. And yet, 3 out of the 10 trials would have led us to conclude the exact opposite thing, right? And again, you see this a lot when you have you do a political poll or something like that, and there's enough variation going on that you get a misleading result. You think that an election is going to turn out one way, and yet it turns out the opposite way, because the difference between what the two candidates get, right, is sort of overwhelmed by the variation. And that gets into the last piece here, letter C. Why do you think taking samples from these two particular populations leads to less conclusive results than in the first study we looked at in this lesson? So keep in mind, in that first study where we were looking at heights of 15-year-olds versus heights of 8-year-olds, right? There, every one of our samples, all 10 of them, led us to the correct conclusion, which was that the mean height of 15-year-olds was greater than the mean height of 8-year-olds. Why is that not the case here? Pause the video now and see if you can write something down. Well, it basically boils down to this. The difference between the two means, right, 55 versus 50, which is only a difference of 5 years, is small compared to the variation within the two groups, which is 10 years, right? So anytime that the variation within the two groups, right, is too large compared to the difference, it's hard to trust the results of what the samples are telling you. So it's because the difference in the two means is small, or mol, is small compared to the variation in the groups themselves. Right? And this is a very deep idea in statistics, right? Within any population, you're going to have variation, right? And that variation can be measured by the IQR, or in this lesson, the MAD, right? And then between two groups, you're going to have also variation, you know, the difference in these means, okay? And it's when the difference between the two groups is small compared to the difference within the groups, right? Look at how similar these two distributions are, with this one definitely a little bit further to the right than this one. But there's so much variation within the group that it's very, very easy to then pull out a sample from this group, pull out a sample from that group, that then misleads you about which population has the higher mean. All right, so let's see if you can kind of get this idea in one final exercise. Exercise number 9. In each scenario, a study is described along with the results from 2 samples. State whether you believe that the sample results are significant enough to justify making an inference about the populations. All right, so letter A. Malik is trying to answer the question, are travel times greater for students who walk to school than students who ride a school bus to school? He takes a sample of 30 students each and finds a mean time of 18 minutes for those who walk and a mean time of 14 minutes for those who ride the bus. The mean absolute deviation for both sets was 7 minutes. All right, so this is a fair hypothesis, right? Kids who walk to school, maybe they have a longer trip to school than people who ride a bus, right? So, you know, he then does this study. He finds that the mean for those that ride the bus is 14 minutes, for those who walk is 18 minutes, and the mean absolute deviation is 7 minutes. So what do you think? Is that data enough for you to then extend the samples to the population and go, I bet if we actually had the populations, we would see that the average for those people who walk to school is longer than those people who ride the bus? Pause the video now and think about that. And the answer is no, it's not significant, right? No, not significant. And that's because the difference in the means is equal to 3, which is smaller than the MAD. In other words, since the variation is large compared to the difference in the two means, we can't extend our sample to the population. There's too much variation. We could do a completely different sample and find the opposite results in terms of those differences. Let's take a look at letter B. Skylar is trying to answer the question, do lemons weigh more than limes? She takes a sample of 25 lemons and 25 limes and weighs them. She finds the lemons have a mean weight of 98 grams and the limes have a mean weight of 65 grams. The mean absolute deviation for both samples was 8 grams. All right, great. So the question is, are these results enough for Skylar to now be able to say, hey, look, lemons in general have a greater average weight than limes? Pause the video now and see what you can say. Okay, and now the answer is a definitive yes. Okay, yes. And here it's because the difference in the sample means is equal to, what is it? I guess it's 33 grams. Hello, red. Is equal to 33 grams, which just really wants that red, which is much greater than the MAD. I wish I could turn it on red mentally on command, but I can't. All right, so yeah, the difference in the sample means is equal to 33 grams, which is much greater than the MAD. In other words, since the difference between the two sample means is so large compared to the variation in the group, as measured by the mean absolute deviation, you can now feel comfortable that what you're seeing in this sample can be extended to the populations as a whole. All right, let's summarize all this. This is a very deep idea, right? But let's start from the basis, right? You have a statistical question. You have to answer it. All right, maybe this statistical question is trying to compare two populations, but it's impossible to get the two populations. So you have to take a sample from one and a sample from another. The question is, can you take those two samples and then conclude something about the populations based on the samples? And it really boils down to how different are the sample means compared to how much variation is there within the sample. If the difference between the sample means is large, a large number compared to the variation, then you can feel comfortable that you can conclude something about the populations. On the other hand, right, if the difference between the two sample means is small compared to the overall variation in the samples, then you can't conclude anything about the populations. And that's a really tricky idea. It really is. And hopefully some of this kind of gave you a sense for why that was. We'll get into this a little bit more in a final lesson where we compare results of two samples. For now, I just want to thank you for joining me for another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.